Good morning, everybody, and welcome to Physics of the Universe. We're still in Unit 19, Part 7. This time we'll be talking about moisture, clouds, and precipitation. Now, this is only going to be Part A because I want to keep these things rather short. So I'm going to have to break these up. We're going to talk mostly about moisture in the atmosphere today. As far as I'll start off with moisture, the water in the atmosphere, and more importantly, how water changes state. When I say changes state, the state in which it's in. Is it a solid? Is it a liquid? Or is it a gas? There's a term that we use a lot in the weather business, which is called precipitation. And basically what precipitation is any form of water that falls from a cloud. It's not too different from the precipitation that you remember back from chemistry. In chemistry, remember, you have precipitates where you had a solid that formed out of a solution. Really what happens in a cloud is a solid forms from the solution of the cloud. So in a cloud, you get a precipitate or an ice crystal that becomes too heavy to hang out in the cloud and eventually will fall out of the cloud. Most of the rain that you see in the sky, like in this picture right here, when it leaves the cloud, you are looking at snow first, then it turns to rain. If you've ever taken an airplane anywhere on a day that it's raining, you'll see that it's raining at the surface of the earth, but as you start to fly higher and higher and higher, you'll see that rain turns to snow. And that could even happen in the summer. Now, there is times where clouds are just rain droplets, and the rain droplets become too heavy and they fall out of the sky too. When we're talking about the weather, though, this is one of the most important processes: is understanding how moisture is behaving inside of that weather. So let's talk about the changes in state. We have solid to liquid. That's the process of turning from ice crystals to liquid droplets. So in order to do that, this should not be new to anybody. In order to turn something solid into something liquid, you're going to have to add heat to it. So we have heat. There's heat in the air right now. We call that latent heat. So what are we going to have to do to that solid to turn it to liquid? Well, we're going to have to take that latent heat and we're going to have to put it into that solid. We have to add heat to that system. So if you have a chunk of ice, in order to make the ice melt, you must add heat to it. That's important. Are we going to be adding heat? Or are we going to take heat away? We have liquid to gas. We have to go from liquid to gas. This is typically it's called evaporation. I will probably be calling it vaporization, because vaporization really is a better way of describing anytime you go from a liquid something to a gas. Vaporization, where you have a liquid like water and you add heat to that. If you add enough heat to that, that water starts to boil and it turns into a water vapor. And remember, it doesn't have to boil. It can turn into a vapor just by the sun shining on it. Then you have condensation. Now, condensation is where you have water vapor in the air. There's water vapor in the air right now. Water vapor in the air, and this time, instead of adding heat to it, we're going to take heat away from it. We're going to cool that air off. When I say cool, remember, there's no such thing as cold. There is only the absence of heat or the presence of heat. If we remove that heat, then the water vapor can't hang out in the air anymore. And when it can't hang out in the air anymore, what it'll do, it'll start to condensate and turn into liquid. So this is called condensation. There is a couple of other scenarios that maybe you're not too familiar with. It is possible for a solid to become a gas without becoming a liquid. You're like, oh, Mr. Lee, how could that happen? You can't take ice and have it turn into a gas. Well, I say yes, you can. And you've probably done this in the refrigerator. If you've ever taken ice, you froze the ice in the refrigerator, and then I know sometimes I put like some ice in the refrigerator and I won't use ice for a very, 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 very long time. What will happen is that ice will start to disappear. And you kind of think that it's shrinking. It's not shrinking. What's happening is it's not melting, but it is eventually giving off little bits of water into vapor form. So it's going strictly from a gas state to a water vapor state. I'm sorry, a solid state to a water vapor state. I said that wrong. We go from a solid state, ice, to water vapor in the air. And you know this happens because if you've ever opened up your freezer, you might see a fog kind of coming out. That's all the little droplets of water that have sublimated, and now it's hitting the warmer air and condensating as it comes out. Probably the most common, though, is, if you think about this, for those people who have seen dry ice before. If you take dry ice, they call it dry ice because it doesn't get wet. That's frozen carbon dioxide, and frozen carbon dioxide doesn't melt, it just vaporizes. That is a form of sublimation. Deposition, kind of just the opposite, going from water vapor to become a solid without becoming a liquid first. So you don't go from water vapor to liquid to solid, you go all of a sudden from water vapor in the air to something solid. So how do you do that? Well, actually, that's something that you should very well be familiar with anytime over the winter, where you've woken up in the morning and there's frost in the ground. Well, that frost is water vapor. Where did that frost come from? Well, that frost was in the air. And if it was in the air and the temperature dropped down so cold, it froze onto the ground. This is called deposition, and it never was a liquid form. Now, I want you to take a look at this chart right here. And this chart right here has something I actually want you to get to know. Here you have a solid, a liquid, and a gas. And I want you to be able to tell me how to go from one to the next. So when you guys go to take this test, in the test, there's going to be a blank one of these charts, and you're going to have to tell me what is the process of going from one to the next, and telling me if heat, is it being absorbed or is it being released? For example, if you're going from a solid to a liquid, this is a common word. I mean, you guys should know what this word is, melting. So you go from a solid to a liquid, that's melting. What's important that you know is that in order for ice to melt, you have to absorb that heat. The water has to, that solid ice has to absorb heat from the environment in order to turn it to a liquid. And then from a liquid to a gas, once again, evaporation, or you can use vaporization. And once again, you're going to have to add heat to that. Now, when you sweat, you stay cool, right? Well, the reason why you stay cool is that when you sweat, the water starts to evaporate. And in order for the water to evaporate, it must steal heat from somewhere. Where does it steal the heat? It steals it from your body. That's why you're cool. You sweat so that water evaporates and pulls the heat away from your body. Conversely, if we go the opposite direction, if there's water vapor in the air, now you can't see the water vapor in the air, but we know that it's there. If you have water vapor in the air and we start to cool that air off, then what you get is something called condensation. Condensation is, well, if you have a nice glass of soda pop or something like that, and it's really cold, maybe you have ice in there and stuff like that, on the side of the glass, you'll see little droplets of water start to form. Well, that's because the glass has gotten colder than what the air can handle. It's removing, that cold air is removing the heat from the air, and water is starting to condensate on the side of it. And if that glass was even colder, you could actually get a freeze. Some drinks you can actually get below freezing, and you'll get a nice little rind of solid liquid on the outside, and that's going from gas to liquid to solid. But in order to do that, you have to release heat from that substance. So in order to get the water vapor out of the air, we have to cool the air off. We have to remove that air. Then there's sublimation, going from solid to gas. Once again, you're going to have to add heat. Believe it or not, in your freezer, there is a little heat that is being added to the ice in order to turn it into a gas. Or if you're going from a gas, if you have it release that air, the air releases the heat, you're going to get something called deposition. Okay, the big thing I want to talk about today is something called humidity. Humidity is a general term for the amount of water vapor that's actually in the air. When the air becomes saturated with water vapor, then it can't hold that water anymore, and it starts to condensate out of it. And this is really important to know, is that the warmer that the air is, the more water vapor it can hold. So if you have cold air, it's going to get rid of the water vapor faster than it would be on a hot day. There are two different types of humidity. The first one is absolute humidity. Absolute humidity is the actual measurement. So if I took a parcel of air and measured how much water was actually inside of it, then that would be, each and every little molecule, that would be a measurement of absolute humidity. And that's not something that we actually use in weather because it's actually not very useful. Something that we actually use is called relative humidity. And relative humidity, I have made a video, and I'm going to show you guys this little video. Just a second here. I went out to my hot tub and I've created this video, and let's hope this plays.
Okay, everybody, I'm out here to talk to you guys. I'm out here at my hot tub in my backyard. I want to talk to you guys about relative humidity. Relative humidity is a way of measuring how much water vapor is in the atmosphere. Now, you have two different types of humidity. You have what's called absolute humidity. And that's if we were to take a parcel of air. A parcel of air is like a little package of air. And we actually counted every little water molecule inside of that parcel of air, and we got a number for it. To be honest with you, nobody ever really uses absolute humidity because it doesn't actually fit with how we understand weather and how we relate to the weather. What we use is what's called absolute humidity.
I meant to say relative humidity. So relative humidity is what I'm talking
measure
about.
of how much moisture actually is in the air, how much water vapor is actually in the air, as compared to how much water the air can hold at that temperature. So that's a little bit complicated. It turns out that if it's hot, if the air is hot, it can hold a lot more water than when the air is cold. For example, I have 3 glasses right here. The reason I'm at the hot tub is I'm going to fill the glasses up with water. So here I've got this cup right here, and I filled it up, and you can see it's not 100% full. So this glass right here represents how much water a glass can hold at a certain temperature. So the volume of the glass represents the temperature. So wrap your head around this. So let's say that this glass is a nice, comfortable temperature, and there's a lot of water in it, so we would say it has a high percentage of relative humidity. In this case, we're looking at probably about 90% relative humidity. And let's say it's a nice, comfortable temperature at the beginning of the day. As the day progresses, the temperature starts getting warmer and warmer and warmer. So I'm going to take this water and I'm going to dump it into this. This glass represents how much water the air can hold at this temperature. So notice I dumped all the water from this glass into this glass. Now you'll notice it's the same amount of water, so the actual humidity stays the same. But now we're down to about 60% of actual filling up this glass. So this would be called 60% relative humidity. Okay? So let's say the weather starts getting cold. We have the same amount of air, and now the weather drops down to, I don't know, close to freezing. So the weather drops down close to freezing. I'm going to do this over here. Now what's going to happen is I'm going to pour this water in, and now we're going to hit 100% relative humidity. Okay, 100% relative humidity is what's called dew point. Dew point is a point of saturation. The air becomes too saturated. And at this point, a couple of things will happen. I still have more humidity. I've got to dump this in. And if the air can't go, you can't go past 100%. If you can't go past 100%, that means the water starts falling out of the air. What does that mean for humidity? Well, you hit 100% relative humidity, then that means that the air can't hold it as water vapor anymore. So it turns into condensation. It turns into little droplets of liquid. And those little droplets of liquid you can find up there. Those clouds. Those clouds are examples of what's happening with condensation. These clouds that we're looking at right now, these are what's called cumulus clouds. These clouds that we're looking at right now, this would be a classic example of, it's a kind of warm day. Warm day. At the surface of the Earth, the warm day can hold quite a bit of water. But it's not 100%. So it might be warm and kind of humid. Not quite 100%. But if we start moving away from the Earth, remember we said the Earth is the thing that's responsible for heating up the Earth. As we get further and further up into the Earth, away from the Earth, like an airplane flying to the sky, the airplane gets colder and colder and colder. Well, if the air is getting colder and colder and colder, then the air can't hold that moisture anymore. So what's happened up there in the clouds is this air that's being lifted up into the clouds is not able to be held at that temperature, and those clouds are hitting dew point. The very bottom of the clouds is the dew point temperature, the temperature in which we have reached 100% relative humidity. And if there's more moisture in the air, what's going to happen is that moisture is going to keep pumping in, and it's going to start to rain. Okay? Now, you might have noticed that summertime and wintertime is a little bit different with your house. In your house, let's say in the wintertime, you might notice that in the house that your skin gets really dry. Everything's really dry in the house. Why is that? Well, outside it might be raining. You might be at 100% relative humidity. The same air that's outside is going to get pumped into your house. Well, if your house is at a nice, warm, comfortable temperature, then you're at a really low relative humidity, which means it's going to be a lot drier. Same air, but it's going to feel a lot drier in the house. The opposite is a problem that they have in, like, say, caves or cellars, places that are cool. So it could be a nice hot day outside, nice hot humid day. By the way, this is not comfortable. A hot humid day outside is 100% relative humidity. That means there's not a lot of room for us to add moisture to the air. And if there's not enough moisture in the air, your body starts to sweat. And as your body starts to sweat, it needs to evaporate to pull the heat away from you to cool you off. Well, that's not going to happen if the air is saturated. So you just wind up getting hot. This is why you hear people from the south saying, it's not the heat that'll kill you, it's the humidity. Well, the humidity is a problem. It could be 90 degrees in Louisiana with 98% relative humidity. And you try to sweat to cool off, and you're not going to cool off. But if you're in Arizona where it's dry, and you're at 90 degrees, well then, it's 90 degrees, but you're in the desert, there's very little humidity in there, you can sweat like crazy, and that's going to cool you off. So 90 degrees in Phoenix versus 90 degrees in New Orleans, two totally different things. But let's go back to talking about what was going on with the wine cellar in your house. In your wine cellar in the house, you might be, like 80% relative humidity. So not enough to rain, but enough to be warm outside. But that air gets pumped into your house, and when that air gets pumped into your house, you're going to hit 100% relative humidity. That's not going to rain into your house. But what it is going to do is it's going to condensate on the windows, on the walls, any kind of bottle that you have, and it's going to turn into water and then possibly even drip down. And this is why places like cellars, at the lower parts of the house, have such a hard problem with moisture. So that's it. That's what relative humidity is. Hope that was useful for you.
Okay. Oop, no, we don't want to watch that again. So relative humidity is just a ratio of looking at how much water vapor is in the air. But the air can only hold so much water vapor. And that is, it's not the same for all air. Cold air can't hold that much water vapor. Warm air can. And how we feel is completely different. So if it's warm air, it can hold a lot more moisture. If it's cold air, it can't hold as much moisture, so it hits high relative humidity sooner than, say, warm air. Now, how do we measure that? And this is one of the most unfortunate things. I tried to get into the school today to go grab one of these and show you guys how it works, but I was not allowed into the school. So I've got a picture of it. This is called a sling psychrometer. And what you're looking at here is you put a little sock on there. You have a dry side and you have the little sock, you get that wet. And you take this thing and you spin it around. Now they're both reading the same temperature when you start off. But as you start to spin it around, the one that doesn't have the little wet sock on it will stay about the same temperature. There's no reason for it to change temperature. However, the one that does have the little wet sock on it, what happens is the water starts to evaporate. And as that water starts to evaporate, it's pulling heat away from the thermometer. Now, the air around you right now has humidity in it. How much humidity it is in it? Well, if it pulls more moisture from that sock, that means the relative humidity is actually low, and there's a lot of potential to put more humidity into the air. So you're going to get a big temperature change on the wet thermometer. If the relative humidity is really high, let's say we had 100% relative humidity, then the water on that sock is not going to be able to evaporate. And if it can't evaporate, then the temperature on the thermometer won't change. So you'll have little to no difference between those two. So that's just our way of going through and measuring. And when we're not in a COVID crisis, I have a lab where you guys would actually go around and spin the psychrometers and figure out what it is. Unfortunately, this year we won't be able to do that, but you kind of get the point. Dew point, we talked about the dew point in the video. Dew point is when you reach 100% relative humidity. So there is, I don't care what athletes say, you cannot give 110%. There's no such thing as 110%. 100% is 100%. So once you have reached the amount of water vapor that air can hold at that temperature, when you reach the maximum, that's 100%. When you get anything higher than that, you can't go higher than that. Anything higher than that is represented by condensation. So if you have 100% relative humidity and then I breathe into that 100% relative humidity, what's going to happen is you're going to get too much humidity and the humidity will start to fall out of the air. If it's up in the clouds, it'll probably undergo deposition and become ice crystals. If it's you've probably done this in the winter where you've been outside, the humidity was really high, and you breathe like that. You have a little bit of water vapor that comes out of your mouth. It hits the air and it turns into little droplets. And those little droplets are really, droplets and ice crystals. That's what clouds are. You've probably been in a fog before. When you look at a fog and you look really, really closely, you'll see the fog is just little droplets of water that are floating in the air. That's because the air has hit 100% relative humidity. And if we keep adding more and more and more moisture to it, those little droplets get bigger and bigger and bigger until they can't defy gravity anymore and they fall down. And that's where we get things like rain. Now, it's important to point out that there's not a magic temperature. You can't say 65 degree is dew point. The temperature for dew point is really dependent on what temperature or how much water vapor is in the air. If you have a very small amount of water vapor in the air, you're going to have to get that temperature really, really cold in order to reach that dew point. However, if you've got a large amount of water vapor in the air, it's going to be easy to reach that dew point. And that could explain why you have high clouds versus low clouds. It's because the water vapor is having to go up further to reach that dew point. All right, that's the end of this one. Next show I'm going to have you guys, we're going to talk a little bit about clouds and cloud formation and the different types of clouds. So that should be pretty interesting. So hope you guys are all taking care, staying well. Love you guys all, and have a good one.